So if you are hand copying in Zoom today, this is your first slide. I'll give you a few moments to copy it down, and then I'll talk about it, what it means, and what our goal for today's lesson is. So hand copiers in Zoom, here is your first thing to copy. Okay, so for this unit and the last unit, when we did systems of equations, one of the bigger goals of both units was to explore different methods for solving a system. So if you had two equations that had two variables, x and y, your solution to that system would be a point, right? X, Y, it'd be an ordered pair. And then when we did a system of three equations with three variables, the solution would be an ordered triple. It would be an XYZ point. And we've done different ways for finding those answers. We've done graphing, substitution, elimination. This unit, we've done matrices where we set up an augmented matrix. We triangularized the bottom corner, got zeros, so we could solve for Z and then back substitute. But still the point was getting the solution. Today we're doing a whole other method. And this method doesn't use any of those other things. This method just uses determinants, which was what we did last Wednesday. And so I will review throughout the lesson and remind you how to calculate a determinant. And then I will show you this method for using determinants only to find your solution. And that method is called Cramer's rule, which is the name of the notes for today. What we have on this screen is a general linear system. So we have two equations. General meaning there's no actual numbers, right? Everything is variables, but it's an XY system. It's two equations, it has two variables. And one thing I want to do to begin is rewrite that system with matrices only. And we've done this one other way with an augmented matrix, but this way is going to be different. And the way it's going to start out is with a coefficient matrix. So I'm going to make a matrix with just the coefficients from the x's and y's. So the first row will be A and B, and the second row is C, D. So this is a coefficient matrix. And right next to that, I'm going to put a matrix for the variables x and y. That's my variable matrix. And then that's going to equal another matrix made up of the constants on the right-hand side of the equation. So that's my constant matrix. And this kind of makes intuitive sense, right? A coefficient matrix, a variable matrix. But I'm going to write some stuff in blue, and this isn't really part of today's lesson. So if you don't want to write down the stuff I'm about to write in blue, that's okay. I just want to remind you of something that has to do with matrix multiplication. So again, what I'm about to write down isn't part of today's lesson. It's just a little review of some stuff we did before. When we multiplied matrices, we talked about how it's the rows in the first matrix times the column of the second matrix, and you multiply corresponding entries. So the first entry in this row would get multiplied by the first entry in this column, and in this case that would be AX. And then we would multiply the second entry in the row times the second entry in the column. And we would add them. Remember, we talked about a thing called the dot product? Well, obviously, if we have this matrix equation set up, that's going to equal the first entry in this constant matrix. And I want to point out to you that that is exactly the same as this first equation that we had in the linear system. And so that's why this matrix setup that I've shown you, a coefficient matrix times a column variable matrix equaling a column constant matrix, why that works is because of the way we've defined matrix multiplication, okay? But again, that was just a tiny review of some other stuff, and it didn't have to do with today's lesson. But it is kind of important so that you know why this format with these three different matrices works in an equation. All right, so I don't actually want that one. Let me get all that stuff off. Okay, so keeping all this in mind, let's go to the next slide. Okay, Zoom, if you're hand copying, actually, I want you to I want to talk about this slide first. So if you're hand copying in Zoom, copy this slide next. No, don't copy that. Sorry, I changed. No, I changed back what I said. Copy this slide. I apologize. I thought I was going to wing it, but then I like this way better. I'm going to stop talking. If you're hand copying in Zoom, here's your next slide. Hey, Janara, we're just taking notes already. And you have a test on Friday. All right, so there's some new notations going on this screen. I told you at the beginning of the lesson that our goal for today is to find the solution to a system using determinants only, okay? What's happening on this screen is we're defining three different kinds of determinants. One that's just plain old capital D, one that's capital D with a subscript of X, and one that's capital D with a subscript of Y. These are going to be our three main determinants for this 2x2 system to solve for X and solve for Y. But I want to talk about how we form those determinants. The first one, just the plain D, is a determinant, and we know it is because of the straight bars. We talked on Wednesday about how the straight lines instead of brackets means you're taking a determinant. And then the values inside the A, B, C, D, this is the coefficient matrix. So capital D is the determinant of the coefficient matrix. And I'm going to rewrite that from the other screen here. I'm going to rewrite that we had the coefficient matrix times the variable matrix, and that equaled the constant matrix. Okay. The second determinant we're going to be working with, the D sub x. It's still a determinant, so we still have these straight lines. But the first column is EF. Okay, that's the constants. So if we take these constants over here, the EF, and replace the first column here, but leave the BD alone, that's how we get this determinant right here, okay? The constants replaced the first column. And remember, the first column represents the x's, the coefficients of the x's. So D sub x is when the constants replace the first column. So what's going on here is that constants replace first column. Okay, that's the x column anyway. So that's why it's D sub x. And then if that's what D sub x is, you can probably figure out what D sub y is. D sub y is when the constants replace the second column, because the second column represents the y's. And so that's what's happening in this third determinant. The first column of the coefficients stays the same, it's AC, but now the constants are in the second column. So the first column remained the same from the original coefficient matrix, and the second column is now EF. So what's happening here is that constants replace the second column, which is the y column. And that's why this determinant has a subscript of y. And so the cool thing that happens once you find these three particular determinants is you can use them now to solve for your x and y. So that's on this next slide. So Zoom, take a minute and copy this slide. So here's how we find x. We take that determinant with the subscript x, where we just use the constants to replace the first column. Whatever number we get there, we divide it by the regular d. And to find y, we take the d with the subscript y and divide it by regular d. So if you remember on Wednesday's lesson, when I first showed you determinants, we just got a number. We did the down diagonals minus the up diagonals. It gave us a number. And I was like, this doesn't really mean anything today, but it will mean something on the next lesson. This is that next lesson, okay? We're gonna find the determinants, find what their values are, divide them in this manner, that's on this screen, and then we have our answer for x and our answer for y, okay? But one thing I do need us to write down on this screen. So the sentence on here says, if d does not equal 0, Okay, that's the capital D, the plain one with no X or Y. Then the system has exactly one solution, and the solution is this. But I do need you to write this down. If D does equal 0, then no solution exists. Because you can't divide by D. And so, I mean, you can't divide by 0. So if you're trying to do these two little division problems right here, and D was 0, you wouldn't even be able to do it because it's undefined. If D does not equal 0, there's a solution. If D does equal 0, there's no solution. All right, and we're going to do an example problem of this. All right, Zoom, take a minute and copy the screen down. I think I said screen. That was weird. Screen. I don't know, with the mask, maybe you couldn't tell. All right, so the first thing I want you to do is to rewrite this in the matrix form that I showed you at the beginning of the lesson. So you want a coefficient matrix. The coefficients are the numbers in front of the x's and the y's. So 2, -3, 1, 4. And then you want your variable matrix next to that. And then the constants on the right side. So your regular determinant D, capital D stands for the determinant of the coefficient matrix. So I do the straight lines to indicate I'm finding a determinant. I put the coefficient matrix inside there. So this is my coefficient matrix. This is my constants. And here's your review for how to find the determinant on a 2x2. It's your down diagonal minus the up diagonal. So the down diagonal is 2 times 4, also known as 8. And the up diagonal is 1 times -3, also known as -3. And we want to add those together. And that gives us 5. So capital D is 5. And we're just going to let that hang out here for a bit. Now, it's good that it doesn't equal 0. If it equaled 0, we would stop right now and say there's no solution. But it doesn't, so we can move on. So now here's the new kind of determinant, the D sub x. This is where so I'm going to do straight lines to indicate a determinant. Remember that the first column on the coefficients represents the x coefficients, okay? The second column is the y coefficient. So to find D sub x, what we do is we take the constants and replace the x column with them. The second column is going to stay the same. The first column, or x column, becomes -923. The second column stays the same. The y column doesn't change. And now we just do our determinant math, the down minus the up. Down is -9 times 4. And up is 23 times negative 3. And we want to subtract those. So negative 36 minus negative 69. Remember that negative becomes plus. So d sub x equals 33. And we're just going to let that hang out here for a bit. And then we do that exact same thing, except now we do it with the y column. Antonio, do you have a question?
No.
No? Okay. So we're going to take the original coefficient matrix, not the one from the d sub x step. Okay? Go back to the original coefficient matrix and replace the second column with the constants. So I'm going to take the constants now and replace this column with them. And this is going to be my d sub y. So I had to slide up here. Sorry if the numbers are going off and you needed them. So dy, I'm using straight bars to indicate that I'm about to find a determinant. The original first column goes back to what it was, 2, 1. But now the constants replace the second column. The constants are negative 9 and 23. And we do the determinant, right? The down diagonal minus the up diagonal. So the down diagonal is 2 times 23, which is 46. The up diagonal is 1 times negative 9, which is negative 9. We want to subtract those. Minus a negative becomes a positive. And we get 55, and that's my d sub y. And we're not done. Like, that was a lot of math, but that's not actually my final answers. Remember, our goal is to find the solution, right? The ordered pair xy. So I'm going to go back to this previous slide for just a moment. In this slide, it said to find x, you do dx over d. Like, whatever you calculated there, you're going to divide those two things. And to find y, you do dy over d. So that's what we're going to do now. And then we'll be done. So here's my things. Okay, there's my d, dx, dy. So x is going to be equal to whatever dx divided by d is, which is 33. Oh, I feel like something's wrong. I did bad math somewhere. Are you ready for me to show you? At the very beginning, when I calculated capital D, that was just the original one, right here. This needed to be 8 minus negative 3, which is plus plus, which is not 5, it is 11. So let's change that to 11. It's going to make our math much nicer. So in case you weren't ready to listen, you were busy writing or something, let me repeat that one time. I made a mistake on capital D, the original determinant. It should have been 8 minus negative 3, which becomes 8 plus 3, which makes our D equal to 11. And so now we can do the calculation for x. dx was 33 divided by d, which is 11. And that's just 3. And then y is dy over d. We calculated dy as 55 divided by d, which is 11, and that's 5. And then our final answer is an xy ordered pair, and that would be 3, 5. And I was going to say, I don't know who's smart enough to see these patterns and come up with these rules, but I suppose we do know it was Cramer, whoever Cramer was. I don't recall, but pretty impressive that the rule was named after this person, Cramer. So that's how to find a solution to a system with using determinants only. I think it seems overly complicated because I'm explaining it while we're doing it. Once you get the hang of it, it just goes like that. Oh, sure, you could use any, if the instructions weren't telling you how to do it, you could use any method that you wanted. It is. That's exactly what it is. Just another method with matrices and using determinants only. We are going to now do one with a 3x3 system, but we're not going to go all the way to the solution for the 3x3 because it would just be, it's very cumbersome and tedious process. What we're going to do instead is spend some time just writing down the notations for a 3x3, and we'll do one example problem where we're just kind of, well, I'll explain it then. For right now, just copy down the screen. It's a lot of letters, yeah. So for those of you hand copying in Zoom, here's your next screen to copy, please. So this is the same screen as the beginning when we were just doing a 2x2. And if you notice, all that's been added is a third variable and a third equation for the z. So here is the next screen that I want you to copy down. And after this, I will begin talking. And for everybody, there is something I want you to add. One statement that I want you to add on this page. This is the same as 2x2, only now replace third column with constants for d sub z. Zoom, please let me know in the chat if you need more time for the screen. Okay, I didn't see anybody in chat. So let's do this problem. So this is the last part of the notes. We have a 3x3 system. We won't be working all the way to the solution because it's just too long and cumbersome. But here's what we are going to do. We are going to write out the determinants for these things. D, dx, dy, dz. And then we're just going to compute the value of d only. And then use that value to say whether or not a solution is possible. Because remember, if d is 0, we would have to say no solution is possible. So we'll just figure that out, and then that's as far as we're going to go. So we're going to set up all the determinants, but not actually evaluate them. The only one we're going to evaluate is d. So let's start by just rewriting the system in the matrix form. Remember, it's not an augmented matrix. It's a coefficient matrix times a variable matrix equals a constant matrix. So you do yours and I'll do mine, and then we'll compare. All right, so there's my matrix forms. Now we're just going to write out each of the determinants, not calculate them. And here's what I mean by write them out. We'll just write d equals, and we'll use the straight lines because that means that indicates a determinant. And then for d, we just fill in the coefficient matrix. 2, -1, 3, 1, 1, 1, -1, 5, 2. And that's all I want to do for write the determinant. For d sub x, straight lines again. And now for d sub x, we take the constants and replace the first column with them. The second and third column stays the same. So write down what you think that looks like. I'll give you a moment to do that before I show you. It's the same as d, but you're replacing the first column with the constants. Okay, there's mine. Does that match yours? All right, try dy. Now, when you do dy, you don't care about dx anymore, okay? You're going back to the original coefficient matrix. And now you take those constants and you're just replacing the second column with them. The first and third columns remain as they were originally. So for dy, I have, and I'm going to read you the rows: 2, 13, 3, 1, 2, 1, -1, -5, 2. And I want you to do dz on your own, please, real fast, without me setting you up? Yeah. The lines you need because it's the thing that saying that it's a determinant. Okay, so I hope you came up with this. So you use the original coefficient matrix, not your dx or your dy version. You take the constants and now you replace the third column with them. So the first column stays the same, second column stays the same, and then third column is now your constants. Okay, and that's all we needed to do for the first part of the problem, is just set those up. The second part of the problem is to actually calculate D, and we're just going to do the one, and this is a review also of how to do a determinant for a 3x3, because it's been since Wednesday that we did that. So we start with the coefficient matrix. And if you remember, the first step we needed to do was to take columns 1 and 2 and copy them over to the right side of the matrix. So we copied those over here. And then we do our down diagonals minus our up diagonals, but now we just have like way more. So the first down diagonal is, so let me write that. Let me just remind you, it's down minus ups. And here's my first down, 2, 1, 2 right here. And we multiply those, 2 times 1 times 2. And that is 4. And then our next down diagonal, and see, suddenly I'm sure your brain is like, oh, I'm so glad we don't have to do this for all the D's. -1 times -1, which is +1. And then 3 times 1 times 5. And that's 15. And I don't know if you remember what we do with those numbers from Wednesday, but we add them. And that just gives us one total number for all the downs, so it's 20. And so when we were doing this on Wednesday, and we were just getting these numbers, and I was telling you, there's no context for this number, it doesn't make any sense, but it will in the next lesson, and this is the next lesson. This is how we use those numbers. And then the up diagonals. So the first up diagonal, -1 times 1 times 3. Or -3. The second up diagonal, 5 times 1 times 2, which is 10. And then 2 times 1 times -1, which is -2. And we're going to add those, and it's 5. So we want to do the down minus the ups, which is 20 minus 5, which is 15. So D is 15. Does that mean yes or no that there is a solution? What did we care about D? We just didn't want it to be what? 0. Perfect. Thank you. So this is yes, there is a solution. If we wanted to find the solution, what we would do is all those downs minus ups that we just did, we would do it for dx, dy, dz, and then we would do dx divided by d. dy divided by d, dz divided by d. And that would be your XYZ answer, but we're not gonna do that. Yeah, like who even, like it's amazing that some people are just smart enough, like they're smart enough and interested. It's not that some people, it's not like we all couldn't be that smart enough. I mean, I think we could, but they're interested enough to like be always thinking about it and like discovering patterns and then coming up with rules, and like that's what their mind is always probably just like, think anything that you like enough that you think about it even when you're daydreaming because you enjoy it like a hobby or whatever, like this would be that for those people, you know.